It looks like there's a terrifying crack in our understanding of the universe. Scientists have compared how fast the universe expands. 2 methods, 2 measurements, completely different answers, and no one knows why. As they dive deeper into this, a new terrifying idea came up. Our entire universe might be spinning. If that's true, it changes everything we know about space, time, and even how the world will end. To understand what's going on, let's talk about how our universe expands. How exactly is it expanding? Into what? We first noticed this about 100 years ago. For many years, people thought the universe was eternal and unchanging. Then came Edwin Hubble. He observed the universe in the telescope and realized the light that came to our planet was coming from galaxies that were moving farther away from us. The galaxies weren't sitting still. The whole universe was moving. And this became one of the most revolutionary discoveries in history. The movement started with the Big Bang. It happened about 13.8 billion years ago. The entire universe, all matter, energy, space, and time burst forth from an incredibly hot, dense point. The bang sent a shockwave, giving all the things and particles their initial boost. That's how they started drifting away from each other. The thing is, they weren't drifting away into open space. No, they created space themselves by drifting. Let's say you're holding a balloon. You draw some dots on it. You start blowing air into it. The balloon gets bigger and bigger. And every dot on its surface moves away from every other dot as the balloon expands. As dots move apart, they basically create space between them by moving away from each other. So the universe isn't expanding into some mysterious space. Space itself exists only within our universe, born between moving dots. The Big Bang boost was so strong that the universe started expanding incredibly fast. It's hard to even imagine. If you were chilling and watching this from the side, it would seem like the entire universe appeared out of nowhere in less than a moment. You wouldn't even hear it because there's no sound in vacuum. There would be nothing. Then you would just blink and bam! The world is everywhere. That bang was so huge that the universe is still expanding from it even now. Even billions of years later, it's space itself that's stretching, with every point on it drifting farther and farther away, including us. We're just moving at a more gentle pace, sort of. So when we figured out everything was expanding, the next question was, how fast? Turns out the movement speed is different for different galaxies. We noticed that the closer things are to us, the slower they drift away from us. And the farther a galaxy is from us, the faster it appears to be moving away. And they're moving constantly. We say, for example, this galaxy is 100 megaparsecs away. But since the galaxies don't actually stay in one place, that means this galaxy is moving at a speed about 4,300 miles per second away from us. If the distance doubles, then the galaxy's speed doubles. So, for example, if a galaxy is 1,000,000 light-years away, it will move away from us at a speed of about 46,000 miles per hour. 2,000,000 light-years away? Double it. Now it's about 92,000 miles per hour. 10 million light-years away? Almost 500,000 miles per hour. Scientists call it Hubble's law. Speed is equal to Hubble constant multiplied by distance, and the Hubble constant is the exact magical speed number that we keep adding up every time we move 1,000,000 light-years farther. So, the Hubble constant is basically the rate at which expansion happens. But there was a problem. A problem that seemed tiny at first, but it was actually hiding a huge disaster. When we measured Hubble constant using 2 different methods, for some reason, we got different results. The first method was to calculate it based on what we see around us right now, today. Different stars, galaxies, their light and brightness. In certain stars, brightness changes in predictable ways. Huge star booms, like supernovas, act like cosmic lighthouses. We know how bright they should be, and thanks to that, we can calculate their distance and speed. It's all clear and simple. But then, scientists tried something totally different. They often use this trick. To figure out how the early universe behaved and then simulate everything from the start, it's like creating your basic characters in Sims and letting them do whatever, hoping that they'll do things in predictable ways and not pull off something wild. We can guess what the early universe looked like because we can still detect the faint afterglow of the Big Bang. We have ultra-precise telescopes that allow us to find an ancient, very first light and very first traces of energy that were born in our world. This post-Big Bang afterglow is literally filling up the entire universe. It's just scattered around like some dinosaur fossils. So we take these fossils and recreate the entire dinosaur based on them. And when we measured what the Hubble constant should logically be, based on how our universe was starting, we got a different number. It doesn't sound like a big deal at first. Based on what we see today, every 3 million light-years away, things are moving about 40 miles per second faster. But based on how our universe was supposed to develop, the number is about 45 miles per second. Literally just 4 miles or so, right? But in cosmology, it's an ultimate red flag. The error bars have shrunk so much that now this isn't just a meh, probably fine situation. It's a literal tension in measurement. And that's exactly what scientists call it, the Hubble tension. It's a serious difference between two super precise measurements based on very different methods, and both of them seem equally right. Imagine using two ultra-precise clocks to check how fast an athlete runs a distance. And in the end, one of the clocks says 10 seconds, while the other says 11. What in the world does that mean? That's terrifying. The two numbers should match, and since they don't, one of three things must be true. First, maybe one of the measurements is wrong, which is very unlikely because both methods are super reliable. Second, maybe something in our interpretation is wrong, but that's also unlikely since many scientists get the same results and agree that the tension is a real deal. And finally, the scariest option? Our entire model of the universe is missing something. That's why scientists are freaking out, and as it turns out, they had a reason to. Recently, a new research team from Hawaii proposed something wild. What if the universe is very slowly rotating? If that's the case, it would be absolutely insane. Here's why. First, if the universe actually rotates, even super slowly, it would mean that the laws of physics might be slightly different depending on where you are or which way you look. That breaks one of our most sacred ideas about physics, that space is the same in all directions. Second, it could mean we've misunderstood the entire cosmic history. Maybe we don't actually know how fast the universe is expanding when it was born, or what dark energy is. That would be a huge disaster. And finally, the most horrifying of all, if it's spinning, then it must spin around something, right? If there's a cosmic axis or rotation, it might suggest a preferred direction. It would be something like cosmic north. We thought there's no special place in the universe, but we might have been wrong. Maybe there's a special place after all. It's like finding out the reality itself has been tilted a tiny bit the whole time, and we just noticed. Right now, we're in an exciting and scary place. Either we'll discover new physics and maybe something about dark energy, or we'll find a subtle error in one of the measurements. Or who knows, maybe something totally unexpected will show up. In any case, solving the Hubble tension could revolutionize our understanding of the universe's origin, structure, and our place in it.
Guess what? The universe can get actual scars, just like when you fall off a bike. Well, here's why. Before the Big Bang, the universe was extremely hot, dense, and full of energy, and it seemed like everything was going well, until that all changed about 13.8 billion years ago. Then the universe exploded. After the blast, it expanded incredibly quickly. Our human brain can't even perceive how fast that expansion was. Sometime later, the universe started cooling down. As it did, giant, terrifying scars cutting through space-time appeared all over the place. And if we study these scars well, We can even get insight into time travel. These days, we call these scars cosmic strings. They're like stretch marks that appear when the skin expands too quickly. Or we could also compare them to cracks that form in the ice when it freezes. These strings are likely very thin, about the size of a proton, a positively charged subatomic particle. Yes, subatomic means smaller than an atom. The strings are also extremely dense and can stretch for light years. Now, imagine these cosmic scars floating through space, not interacting much with their surroundings. When two cosmic strings pass each other, they could warp space-time in such a way that it creates a time machine. If you were to travel along a certain path around these strings, you would end up returning to your starting point at an earlier time, which is traveling back in time. Now, let's admit it, this idea sounds like something from science fiction, but it's supported by cosmic string theory, and the math behind it seems to work. Unfortunately, no one has observed cosmic strings yet, so for now, it's still a theory. In 1991, one physicist proposed an idea for how cosmic strings could enable time travel. If two infinite cosmic strings passed each other in parallel, they would warp space-time, creating a time loop. This loop would allow someone to travel back in time. Even better, this idea doesn't contradict Einstein's theory of general relativity, which suggests that large objects can bend space and time. These bends in space-time could allow a shortcut through time. His now well-known concept of closed time loops also helps explain how wormholes might work. So, a wormhole is basically a theoretical tunnel connecting one place in space to another. Some people believe that by using such tunnels, we could create shortcuts for incredibly long journeys through the universe, which would allow us to visit other star systems and galaxies. So, let's say you manage to create a wormhole and even accelerate one of its ends to near the speed of light, and then you send it back to where it came from. Well, at that moment, those two ends are not synced anymore. One is in the past, while the other is in the future. And if you somehow manage to walk between them, you'd be time traveling. You could do something similar by placing one end of the wormhole near a powerful gravitational field, like a black hole, and keeping the other side near a weaker gravitational force. This way, according to the theory of relativity, time would pass more slowly nearer to the strong gravity side, and it would allow a particle or another chunk of mass to remain in the past relative to the other side of the wormhole. At the same time, if you decided to create a wormhole, you'd have to keep in mind that they are super dangerous. They might collapse all of a sudden. They're likely to be highly radioactive, or you could come into contact with toxic exotic matter inside. But let's get back to the math behind the cosmic string time machine idea. Admittedly, it is solid, but it doesn't mean such a time machine is possible yet. To use this way of time travel, we'd need to reach near light speed, and it might be impossible. According to Einstein's relativity, the faster an object travels, the more energy it needs to continue speeding up. In other words, we don't yet have the technology or energy sources to accelerate a spacecraft to these speeds. The idea of two infinite cosmic strings is also questionable because we can't create something that's infinitely long. So, while this time travel model is mathematically sound, the infinite nature of the strings would make this exact model impractical. At the same time, some scientists still believe that cosmic strings are a better possibility than most other models, like wormholes. In any case, before we can start considering time travel, we need to discover cosmic strings. Luckily, there's a group of astronomers working to detect low-frequency gravitational waves by measuring signals from a type of star called a pulsar. Now, pulsars send out regular pulses of radio waves, and by measuring small changes in the timing of these pulses, scientists can detect subtle shifts in space-time. Those changes are caused by gravitational waves, which are ripples in space-time. Now, so far, we've only detected gravitational waves coming from black holes. But in 2020, there was one strange signal that didn't look like it came from black holes. It could be coming from cosmic strings. And here, we need to mention string theory. According to it, the universe is made up of more than just the 4 dimensions of space-time. There are additional dimensions that are hidden from us. Plus, the basic building blocks of the universe aren't particles, but tiny vibrating strings. These strings can vibrate at different frequencies to create different fundamental particles. These strings, from string theory, could have stretched out during the early universe and become the very cosmic strings we've discussed. In the coming years, we might get more information about them from a space-based gravitational wave telescope called LISA. It's supposed to launch in 2035. But if the signals picked up in 2020 really came from cosmic strings, it could mean a huge breakthrough in physics. In this case, string theory would become the right framework for understanding the universe. It would completely change the way we think about the building blocks of our reality. On the other hand, even if the signals don't turn out to be from cosmic strings, this discovery would still be important. It would give scientists more information on what cosmic string signals might look like in the future. And while we're not yet at the point of time travel, the discovery of cosmic strings could take us one step closer to understanding the mysteries of the universe and maybe even the possibility of traveling through time. Now, time travel is a popular theme in science fiction, but in fact, moving forward in time happens naturally. Right now, you are traveling into the future at a steady rate of 1 second per second. However, scientists have discovered that this rate can change depending on speed and gravity. Einstein's special theory of relativity explains that time slows down as an object moves faster. The closer you get to the speed of light, the more slowly time passes for you, compared to someone who isn't moving at all. The general theory of relativity adds another factor: gravity. The stronger the gravitational pull, the more slowly time moves. Near massive objects, such as the surface of a neutron star, black hole, or even Earth, time runs more slowly than it does far away from these space objects. If someone were to stay near the edge of a black hole, where gravity is incredibly strong, only a few hours might pass for them, while thousands of years would go by for people on Earth. If they returned, they would have effectively traveled into the future. This is a real and scientifically proven effect. A real-life example of time travel, though on a tiny scale, can be witnessed in space missions. For example, this cosmonaut spent a total of 748 days aboard the space station Mir during 3 separate missions. Because Mir was moving at high speeds relative to Earth, it experienced time dilation. As a result, he aged 0.02 of a second less than had he stayed on the ground. Now, this difference may seem tiny, but it shows that time moves differently depending on speed and location. But while traveling to the future is scientifically possible, traveling to the past is much more complicated and controversial, and leads to logical paradoxes. Imagine you throw a billiard ball into a time machine. It travels to the past and collides with its earlier self. This prevents the ball from ever entering the time machine in the first place. A contradiction.
For decades, time travel has been dismissed as impossible. But this physicist just cracked the code using quantum mechanics. He's trying to prove that time loops might actually exist without breaking reality. So could this be the first real step toward building a time machine? In everyday life, we're used to time moving forward in a straight line. It goes from the past to the present to the future. That's how people saw it before Einstein, because that's how it feels to us. But when Einstein showed up, he told a very different story. He showed that both space and time are woven together like some flexible fabric into one thing called spacetime. Space itself can bend and twist, and time does the same with it. The fabric of spacetime bends and gets curvy when we place heavy objects in it, like planets, stars, or black holes. The heavier the object, the more it will get stretched and bent, slowing down time around it. Movies like Interstellar showed it pretty well, even though the characters only spend a few hours on the planet. When they return to the spaceship, 23 years have passed for the astronaut waiting there. Why? Because the black hole's extreme gravity warps this fabric of space-time itself, and the closer you are to it, the slower things go for you. Sounds insane, but that's how our universe works. And that's not just black holes. All massive objects, like the sun, for example, bend the fabric of space-time around them. This is also why planets orbit in curves. All this gave physicists a pause. If we can bend space-time, can we bend it to such a way that we'll make a loop out of it? It would be like going on a journey that bends back on itself, meaning that if you followed it, it could return to the past and experience the same moments again. That would be pretty insane. Imagine that you walk down a hallway expecting to exit through the door at the end, but instead of a door, you find yourself standing right back where you started, walking into your past. But just imagine how hard something like that would be to pull off. Yes, heavy objects can stretch and twist space-time, but even those massive things still don't loop time. They just slow it down very strongly. It's hypothetically possible, but it would require super extreme conditions. For example, if the black hole gets a little extra boost, spinning, it could theoretically bend space-time around it into a loop. There are also some wacky ideas, like exotic matter and wormholes, but they're all speculative. But let's assume that there is a way to make a CTC. Creating it isn't our only problem. This is where the paradoxes begin. If a time loop could exist, wouldn't it create contradictions? The grandfather paradox is just one example. If you follow a big loop like that and accidentally prevent your grandfather from meeting your grandmother, you'll make it mean that one of your parents is never born, and you weren't born either. So how could you travel back in time in the first place? Or what happens to you after that? There are other ideas like that, like destroying your time machine before you use it, or giving William Shakespeare his own plays. There are infinite possible paradoxes. All this is happening because of entropy. It's one of the main laws of physics, this idea that chaos in the universe always increases. Things start as something normal and structured, but eventually they break apart, becoming weird and chaotic, and can never go back. Ice melts but never refreezes into its original shape on its own. Our bodies age instead of getting younger. We remember the past, but not the future. All these are examples of entropy. So, if time travel were possible, how would entropy behave? Would a broken glass fix itself? People grow younger, and people would lose their memories? That's exactly how paradoxes like grandfather's paradox are born. Well, this is where the recent theory changes everything. The physicist Lorenzo Gavassino has a cool idea to explain this issue. He tackled quantum mumbo-jumbo, working with something called quantum fluctuations. See, the universe is never completely still. Even in empty space, at the tiniest level possible, there are constant random changes in energy. These are those quantum fluctuations. They're like tiny, unpredictable jitters that pop in and out of existence. Yeah, our universe is just weird like that. It's like a lake. On a normal scale, it looks smooth, but if you zoom in super close, you'll see tiny, unpredictable ripples forming and disappearing all the time. Our universe is the same with quantum fluctuations. These fluctuations happen everywhere, and they become really important when dealing with stuff like black holes and time loops. Now, back to the time loops. Gavassino says that in a time loop, quantum fluctuations mess with entropy in a strange way. Ideally, the chaos should increase. As usual, we're getting older, our spacesuit is getting weary, broken things don't fix themselves, and so on. But it seems like instead of always increasing, chaos in a time loop can randomly decrease. This means things that should be irreversible, like aging or breaking something, could actually reverse themselves. So yep, if you try doing something wild during time travel, it won't really work. If you try to prevent your grandpa from becoming your grandpa, the universe could reverse that change, making it like it never happened. If you travel to the past, your memories could vanish, meaning you wouldn't remember the future you came from. And if you try to break causality, the universe might just remove the contradiction. Time would always find a way to correct itself, preventing paradoxes. Scientists actually suspected this for a while now. Many of them have believed that if time travel were possible, the universe would somehow prevent weird paradoxes. Basically, it would make sure that everything that happens must be logically consistent with itself. Well, Gavasino's work basically gave a mathematical proof of that using quantum mechanics. Of course, there was another wild theory, the one with multiple universes. You definitely saw this in the movies. It says that when we travel back in time and change something, we simply create a new timeline. The old one remains, but this one would go a completely different way. But this idea is more about cool sci-fi than actual math and physics. But does that mean that time travel actually exists? Well, not right now. Even if time loops could exist in theory, that doesn't mean they actually do exist in real life. Stephen Hawking, for example, thought that these time loops are impossible. He said that the universe works in such a way that it would simply prevent time loops from forming. He even organized his famous time traveler party. Unfortunately, no one showed up. But many physicists still believe time travel is impossible, at least on a macroscopic scale. They even kind of managed to do that. For example, teams from Oxford and Vienna wanted to see if they can reverse one single electron back in time. And they managed to do that inside of a quantum computer, though the effect was tiny, only a fraction of a second. Recreating that normally would be absolutely insane. If we wanted to see something like this naturally, we would have to observe 10 billion electrons per second for the entire age of the universe. And even then, we'd only see it once. The more particles they tried to rewind, the more errors appeared. With one tiny electron, it worked well. But when they got to 3, accuracy dropped in half. But even if we never find a way to travel through time, understanding all these things could still help us a lot. It would help us study black holes, the early universe, and even quantum technology. So, while time machines are still science fiction, this research is pushing us closer to understanding our universe.
Time is nothing but a magician's trick. Or is it? We're used to time zipping along like a car, always pointing into the future. It creates cause and effect, lining events up one after another, like dominoes. Sometimes it stretches between moments, getting so slow it might even want to stop. And it's got a spotlight on right now, because that's the only moment that truly matters. But there's a new theory, that it might not exist at all. We usually think of space as having 3 dimensions, up and down, left and right, forward and back. And everyone thought that time was a separate thing, just a universal clock ticking away in the background, and it's the same for everyone. But then Einstein came forward. He decided to surprise everyone back in 1905 when he introduced his special theory of relativity. It said that time is another dimension, just like the others, and they're all tied together in one big space-time. Based on this, it turned out that time can change depending on the speed at which you move. Now imagine that we take 2 twins. Twin A stays on Earth, Twin B takes a journey into space on a spaceship moving at a speed close to the speed of light, let's say 90% of that speed. Twin B travels to a distant star and then returns to Earth. For Twin B, it feels like the journey only took a few years. But when they come back to Earth, it turns out that Twin A has aged significantly more. They find out that 20, 30, or even more years have passed on Earth. That's all because of the phenomenon called time dilation. It happens when we're reaching speeds close to the speed of light, causing time to slow down for the traveler relative to someone who stays in one place. 10 years later, Einstein proposed his theory of general relativity. That's when we learn that time changes not only based on your speed, but also based on gravity. Back in the day, Newton thought that gravity was some magical force that makes objects attract each other. However, Einstein proposed that this isn't a force, but more like an after effect. Picture the space as some huge cloth. When you throw a heavy ball on a cloth, it curves. Now, if you throw some small balls around it, they will naturally approach the heavy ball. At the same time, massive objects like stars and planets cause spacetime to curve around them. When there's something super heavy in spacetime, it curves the matter around it. This curvature tells objects how to move, and this is what we call gravity. This idea created all sorts of cool predictions that later turned out to be true. Bending of light by gravity, black holes, and time dilation around these black holes, just like in Interstellar. This theory revolutionized our view on everything, but we might be on the verge of another revolution. Some philosophers have a crazy claim. They say that the things we believe about time are all just ideas in our heads, not facts of the physical world. This idea, which breaks the traditional view of time, is called the block universe. It's backed up by Einstein's theory of relativity, but extends it and makes it more complicated. Imagine the universe as a huge sandwich. This sandwich contains every moment of time, past, present, and future, all at once. Each layer or slice of the sandwich represents a different moment in time, and all these layers exist simultaneously rather than one after the other. In this model of our world, the past, present, and future are all equal. Unlike our everyday experience, where the past is gone, the future hasn't happened yet, and only the present is real, the block universe says that every point in time is just as real as every other point. Imagine your birth, this moment right now, and what you'll be doing in 10 years from now all exist together in this block. It also says there's not really a flow of time. We're used to time flowing from one moment to the next, even with Einstein's theory. But in the block universe, the feeling of time moving is more about how we experience and remember events than about how time itself works. It's like reading a magical book. All the pages exist at once, but you can only experience the story page by page. Now, this implies some scary things, like destiny, and whether free will actually exists. If everything is already laid out, does what we do matter? For example, you clicking on this video was already predetermined in the block universe. Every choice you've ever made was an illusion. You're just a program following a code, but with an ability to understand its consequences. This would explain why we order junk food at midnight, knowing that it's a bad idea that we're going to regret. But some scientists argue that time's flow and direction are as real as it gets, because cause and effect still exist. If your birth, current moment, and you in the future with gray hair all existed at the same time, you'd be able to visit your past self at any moment, and already knew what your future self is like. So this whole debate might just be about how we piece together our stories of the past, not proof that the future isn't waiting to unfold. There's also a never-ending battle between general relativity and quantum mechanics, which only adds spice to the debate. On one hand, general relativity plays with time like it's a stretchy Play-Doh. The flow of time can stretch or compress depending on the speed or gravity. On the other hand, in quantum mechanics, time isn't something that can be manipulated or changed. It's a constant stage upon which the particles and forces of the universe perform. These two fields have been fighting for a long time now, and scientists are struggling to unite them in one cohesive theory of everything. Although there are some candidates who try to merge them in a logical way, like string theory. Now, string theory sounds scary, but it's simply saying that the entire universe, with all its particles and atoms, is made up of ultra-tiny vibrating strings. Each string can vibrate in separate ways, like the strings on a guitar, and in many dimensions. The way these strings vibrate determines what type of particle they will be, like an electron or a quark. Another idea, called loop quantum gravity, says that space and time are made of tiny loops. Whether it's strings or loops, unfortunately, they would be so tiny that we simply don't have strong enough equipment to check them out yet. So until we test these theories, they can't be proven. What's interesting is that both ideas don't really need time to explain how the universe works. We think of things like tables and chairs as real, even though physics doesn't describe them directly. We say they emerge from the tiny particles that make up the universe. But with time, we're not sure how it would emerge from something else. But no matter what the answer is, you're going to be okay. If it turns out that it doesn't really exist, then it could make everything feel pointless. But think about this. We still lead our lives, and we still experience what feels like causation and make sense of everything. It still feels like it was our choice to order that junk food at midnight. So, does that being predetermined really matter? In any case, we've been wrong about plenty of things we thought were set in stone. Right now there's a big split between the block universe and our traditional theories. But we'll learn the truth over time.
Turns out we have some ways to solve the time travel paradoxes. Time travel sounds enticing, but brings with us a lot of problems. Take, for example, the famous grandfather paradox. Imagine that you travel back in time and prevent your grandparents from meeting. This alters the course of history. But how? If you erase their encounter, you cease to exist, so you couldn't even travel back in time to alter the past in the first place. There's also the bootstrap paradox. Let's say we travel back in time and give Beethoven his own compositions before he ever penned them. He gets famous for the very music you provided. But where did it originate? Did you start it? Or was it Beethoven who started it? There are many theories about time travel. One of them involves alternate timelines and parallel universes, like in Back to the Future, for example. If parallel worlds exist, we could hypothetically travel in one where the events unfolded differently, while our original timeline stays the same. This is a beautiful and paradox-free approach, but this is pure sci-fi, as we have no concrete evidence of parallel universes. So what scientists are trying to do instead is to figure out whether time travel is impossible in this one universal timeline. We've been exploring this equation for over a decade and created a fascinating concept called a closed time-like curve, or CTC. Imagine taking a path that forms a loop, bringing it back to where it started, but in time. We know that spacetime is like a wobbly piece of cloth which can curve and bend when we place heavy objects on it. In some situations, like near massive objects such as stars or black holes, spacetime can be curved. Now imagine an object that's so heavy, with gravity curving the spacetime so strongly that it literally loops on itself. If this idea turns out to be real, it could suggest the possibility of traveling back in time in our world line. This possibility is fascinating, but it also creates tons of problems, and scientists may have found the ways to solve them. One of the solutions is that doing paradoxical things can be simply impossible. In this scenario, we assume that the universe has some mechanisms of self-consistency. It means that while you can still travel in time, you're restricted in the actions you can take. For example, you may not be able to go back and alter your family's history, but there's nothing inherently illogical about traveling back in time to simply interact with your ancestors. In this scenario, the universe only forbids you to do logically impossible things. Scientists decided to conduct an experiment to check if it works, and the results were pretty terrifying. The experiment conducted involved the creation of a theoretical time machine. This is also called an in-principle time machine. This wasn't a physical device, but rather a quantum simulation. In the simulation, they attempted to send a photon back in time by a fraction of a second and make it interact with its past self. The goal was to find out what the photon will do. Will it destroy its previous self, avoid the interaction, or something else? What happened is that as the photon approached its past self and was getting closer to the point of creating a paradox, the experiment tended to fail more frequently. In other words, it seems like the laws of physics or the fabric of the universe might have some weird built-in mechanisms that prevent time travel paradoxes. In that case, the question is, how does the universe understand what is logically impossible? And how does it prevent us from doing these things? Which is quite scary to think about. There's another theory that the universe allows paradoxical things to happen, but also self-corrects them. Imagine a time traveler going back to stop some health condition from spreading. According to this theory, even if the traveler succeeds, this health condition would find another way to spread, avoiding the paradox. Or maybe we all exist in time loops. These loops allow objects to interact with their past selves while still maintaining a consistent timeline, because there's no beginning point. For example, trying to prevent a historical event could result in accidentally catalyzing the event we were trying to prevent. This idea challenges our understanding of classical physics and free will. But all these ideas are purely theoretical, and to test them, we first need to find the mechanism to actually travel back in time. Talking about practical time travel, we mentioned that space-time curves around very heavy objects. Does it mean that black holes can be portals to the past and the future? Maybe. Black holes are formed when a massive star collapses inward. Their gravitational pull is so intense that even light can't escape. This means they're perfect for bending not just space, but even time itself. You might remember this from Interstellar. Near a black hole, time slows down. This effect is so pronounced that a year near a black hole could translate to decades on Earth. In that case, traveling back to the past using a black hole is theoretically possible. If their gravity twists time so much that it wraps back on itself, creating a closed time-like curve, and you could enter this loop, you'd find yourself on a journey from the future to the past. But there are some problems with this. First, you can only travel into the black hole's past. Second, to enter the loop, you'd likely have to cross the event horizon, the point of no return around a black hole. To escape one, you'd have to travel faster than light, which is currently impossible. So, while black holes might hold the keys to time travel, the journey inside one might be your last. But not everyone agrees that closed time-like curves exist at all. Recent research has shed new light on this topic. The results showed that time can only move forward. The research offered a fresh perspective on how light behaves when it encounters different materials. When light moves through empty space, it travels at a constant speed of 186,000 miles per second. But when it encounters substances like water or glass, its speed can change, causing it to bend or refract. While scientists have equations to describe this behavior, they struggled with the problem of the change of the speed of light at the boundary in different mediums. Well, researchers proposed a solution to this puzzle by reconsidering how light moves through time and space. They figured out that it always remains constant as it travels through different mediums. No matter what the light encounters, it always moves forward in time. This means that light and other waves like it follow the same one-way path through time that we do. Another thing is that light also always saves its momentum, and it always stays the same, pointing forward in time. And finally, even with general relativity and with gravity bending light very strongly, it still keeps pointing forward. It can slow down to the point of feeling like time stopped, but never move backwards. This challenges our previous notions about the relationship between light and time. It implies that time has a definite direction for all waves, making it impossible to reverse. However, their equations have only been tested in one dimension, and experiments are needed to confirm if this theory holds true in reality. Stephen Hawking also disagreed with the idea of traveling back in time. He proposed a theory called the chronology protection conjecture. This idea says that the laws of physics stop time travel on large scales, even when theories like general relativity say it's possible, and that closed time-like curves simply can't exist. Hawking said that traveling back in time would mean creating new matter, which goes against the laws of physics. Although we're far from building actual time machines, if we keep diving into mathematics, we might find the truth one day.
A long time ago, we believed that the entire universe revolved around our own little blue planet. It's called a geocentric model. We thought that the sun, the stars, and all those twinkling celestial bodies all danced around us. This theory was super popular in ancient Greece and Rome. Famous geniuses like Aristotle and Ptolemy really loved this idea. Why did people believe this in the first place? Well, first of all, we have a massive ego. Second of all, there were a couple of things that seemed to support it. For example, if you stand on Earth and look up at the sun, it seems like the sun is spinning around us once every day. The moon and the planets seem to be doing the same thing. The obvious conclusion is, oh, they're probably twirling around the Earth. Then there's the fact that Earth feels pretty steady when you're standing on it. It just doesn't feel like it's moving, you know? And because of this stability beneath our feet, people thought that the Earth was unmoving. But even back then, there were ancient Greek and Roman philosophers that were onto something cooler. They paired the geocentric model with the idea that Earth was actually a round ball floating in space, not a flat disk. They started connecting the dots. And after a while, astronomer and mathematician Aristarchus of Samos had a game-changing idea. He thought that the Earth might not be the center of everything. He proposed that everything revolved around the sun. Funny to think that back in the days, this idea was considered insane. That's why for a while, most people stuck to their geocentric views. It took us many centuries to finally accept the heliocentric model, where all the planets in our solar system revolve around the sun. This idea was brought to life by people like Copernicus, Galileo, and Kepler. This change wasn't easy for people. It was hard to let go of our space crown. But gradually, we came to terms with it. And by letting go of this idea, we discovered a whole new world. This journey led us to an astonishing realization. Not only we're not the center of the universe, we're nothing but a little speck in it. We're a microscopic dot, sprawling galaxy called the Milky Way. The discovery of the Milky Way started right from our own backyards. If you've ever gazed up at the stars on a clear night, you might have noticed a faint, luminescent band stretching. It's like a shimmering celestial ribbon woven with stars. That is our galaxy. It was named Milky Way because it looks like someone spilled milk on a road. It was perfectly depicted in the 90s by Voyager 1. NASA's spacecraft took a picture called the pale blue dot. That tiny little pixel that's almost impossible to see is our planet. The photo was taken from a chilling 3.7 billion miles away from the sun. On a universe scale, this distance is nothing. But for us, it's unimaginable. So when scientists discovered the Milky Way, they armed themselves with telescopes. Their goal was to map the uncharted territories of the night sky. And of course, to find our place in this gigantic world. To do that, first, we had to unlock the secrets of our galaxy's structure. Okay, so we can clearly see that it has some band-like formation. That probably means that our galaxy is not a big, round ball, like the planets and stars. In reality, it's more like a giant pancake, a flattened disk. And we can see that we're not above it, and not below it. We're right on the plate. The next step is to travel across the Milky Way to map it. There's a little problem, though. To do that, we'd have to traverse thousands of light years perpendicular to this pancake-like plane. Just to put things in perspective, think of Voyager 1, the one that took the pale blue dot picture. That spacecraft has been journeying through space for almost half a century. It left the solar system years ago. You know how many light years it traveled? 0.002. And how many light years is the Milky Way? 100,000. You get the picture. But the lack of fancy technology didn't stop us. In the 18th century, a bold astronomer named William Herschel decided to explore our galaxy. With nothing but a telescope, this Indiana Jones of astronomy started mapping the stars in the night sky. As a result, he discovered Uranus, more than 2,000 nebulas, and created the first map of the Milky Way that depicted it as a disk. The map wasn't super accurate, but still very impressive. Unfortunately, he didn't know about something called interstellar dust. It's like space fog that can block our view of stars in the center of the Milky Way. This dust made the central region of the Milky Way appear less crowded than it actually is. Now, let's go all the way to the 20th century. Henrietta Swan Leavitt, an American astronomer, was another curious stargazer. But she focused her attention on a special kind of star called Cepheid variables. These stars had a unique quirk. They pulsed, getting brighter and dimmer in a predictable pattern. Leavitt's job at the observatory was like being a librarian. She cataloged these special stars, and in doing so, she stumbled upon something incredible. A direct link between the brightness of these stars and the rate of their pulsations. This discovery is now known as Leavitt's law. It meant that by simply measuring how quickly these stars pulsed, astronomers could figure out how far away they were. These pulsating stars became the rulers for measuring distances. Before the 1920s, most scientists believed that our Milky Way was the only galaxy in the universe. But as telescopes improved, some astronomers started realizing that this isn't the case. We started finding more and more galaxies. But if the Milky Way was just one of many galaxies, where exactly were we within it? Meet the scientist named Harlow Shapley. Armed with a powerful telescope, Shapley turned his attention to globular clusters. These are tightly packed groups of ancient stars that gather together in spherical shapes. That's when he noticed something interesting. The oldest stars around us weren't scattered all over the canvas. They were clustered around the center of the Milky Way, and they were pointing in the direction of certain constellations like Sagittarius and Scorpius. It turns out that the origin of our galaxy began from the center. It was the heart of the Milky Way, and the most ancient guys were hanging out there, which means we're not even at the center of our own galaxy. Seems like our importance becomes less and less with each new discovery, huh? Anyway, Shapley found out that we were positioned somewhere on the outskirts of our galaxy. Shapley's calculations weren't perfectly accurate, but he got pretty close. Luckily, now we have very precise and cool tools. Since then, we've since pinpointed our precise location. We're located near a partial arm of the Milky Way called the Orion Arm. It's about 26,000 light-years from the heart of our galaxy. And that was the story of how we found out where we are in the Milky Way. You think our story is over? Oh, absolutely not. Meet Gaia, the European Space Agency's celestial cartographer. Launched in 2013, Gaia embarked on a daring mission. It has to map the Milky Way in unprecedented detail. Not just some rough map, but a photographer capturing every nuance of our galaxy. Gaia is piecing together the positions and motions of about 1 billion stars, and it's like 1% of the stars in the Milky Way. But even that tiny fraction is enough to create a masterpiece of cosmic cartography. What a grand journey it was. It led us from thinking Earth was the center of the universe to realizing we're less than a speck in the grand scheme of things. But what's more important is that this story shows humanity's drive to uncover the mysteries of the world. And there's always something new to explore. Discoveries just keep coming, so stay tuned and keep looking at the night sky.
Could it be that the entire universe is nothing more than just an atom? When you look at a diagram of an atom, which is a building block for all matter, you can see that some examples of the universe repeat. Our solar system is a great example of that. There's a giant central star and a couple of smaller planets that circle around it. You can observe the same arrangement outside our galaxy too, with exoplanets orbiting their stars. And you can also witness that principle on a smaller scale. It's the way particles called protons and neutrons move around the center of an atom, which is called the nucleus. So imagine you have a bunch of positive magnets you're trying to stack together. They keep pushing each other away, right? That's what's supposed to be happening with the protons in an atom. They're all positively charged, so they should be repelling each other and flying off in all directions. But atoms do exist, so there must be something holding them together. And that something is called the strong interaction or strong force. The nucleus makes up less than 1/100% of the volume of the whole atom, but it usually takes up over 99.9% of the mass of the atom. Once again, similar to our Sun. Anyway, this strong interaction is like a special type of glue that holds the protons and neutrons together in the nucleus of an atom. In a similar way, gravity prevents us from flying away from the ground into the darkness of space. Now, this glue comes from some really smart particles inside protons and neutrons called quarks. These little guys have a strange kind of charge called color. It's not like the colors we see around us. It works like a code that helps quarks stick together inside their host particles. And this code also seeps out and helps hold protons and neutrons together in the nucleus. In a way, quarks are like little builders that are working together to build atoms that make up everything around us. The Big Bang was said to be a magnificent moment when we got time and space. It's the story we use to explain the evolution of the universe. In the beginning, there was only a very, very small ball of matter the size of a peach, but with a temperature of more than a quadrillion degrees. Ow, that's hot! And this bang in the name doesn't mean there really was an explosion in space. This peach started spreading around, and space was just appearing everywhere. It gave rise to atoms, molecules, stars, and many celestial bodies that filled the empty space of our cosmos. Basically, all the elements that make us formed within a few minutes at the earliest stages of the universe. Let's say like 1/100th of a billionth of a trillionth of a trillionth of a second. Oh wait, give me a second to process that. Alright, moving on. The growth was incredible at that stage. The universe spread exponentially and managed to double in size at least 90 times. Like me during the holidays. I love chocolate. After the Big Bang, the universe was a hot and dense soup of particles, too hot for atoms to exist. But 380,000 years later, it cooled down enough for electrons to mix with nuclei and form atoms. This is a process we called recombination, and it's what made the universe transparent. Think of it like turning on a light switch. Suddenly, you can see it all. But just because the universe became transparent didn't mean it was bright. It was a dark period, as there were no stars or galaxies yet, like a big empty canvas waiting for something to be painted on it. It wasn't until much later, as the universe continued to evolve, that stars and other bright objects started to form and light up the darkness. And it went on evolving, all the while filling up with planets, asteroids, galaxies, and other things. Okay, so that's the story we've been told for the past couple of decades, and a pretty good one, I should admit. Scientists have studied it so much. They observed the leftover electromagnetic radiation from the young universe. They measured the presence of the lightest elements only to realize they all line up with the story of the Big Bang. New theories don't say the Big Bang didn't happen. It's a good picture of the cosmos in its early stages, but it's like an unfinished puzzle with some important parts missing. We can't explain what happened before the Big Bang using our current physics, so we need some new math to explain tricky parts, like the so-called singularity. It's the point of infinite density, remember? From the beginning of the Big Bang. And that's where string theory comes in, like a superpowered toolkit that can handle gravity and all other forces combined. Now, one of the ideas that string theory has given us is the ekpyrotic universe. Imagine a big fire that sparks off another fire, and that fire sparks off another fire, and so on. Well, in this scenario, the Big Bang wasn't the beginning of everything. It was just one part of a bigger process. It's the idea of the cyclic universe, a never-ending roller coaster ride with big bangs as beginnings and big crunches as ends, happening over and over again, potentially forever. It's like the universe is constantly hitting the reset button and does it in a really fun way. We could look at this singularity, according to some theories, as a single particle in a much larger system, much like an atom is made up of subatomic particles. And considering all that, The idea says every nucleus of an atom could have a universe inside of it. So our entire universe is just a tiny part of an atom in a much larger universe made of atoms with more cosmoses, with more atoms and more cosmoses. So twisting. The early versions of the idea of the cyclic universe still had one big issue. They didn't match up with our observations of the cosmic microwave background, which is a fossil light that shows how the universe looked when it was only 380,000 years old. So, in March 2020, two physicists from Canada published a study that revealed the math behind the cyclic universe that we missed earlier. If we focus on the moment when the universe shrinks to an incredibly small point and then bounces back to a Big Bang state, we might be able to match up with our observations after all. It's just that we need to wait for more new experiments to fully test the idea. The Grand Unified Epoch, that's what we call the time when the universe was still young. At that time, matter and antimatter, which are like mirror images of each other, existed in roughly equal amounts. But since they are opposing forces, when they come into contact with each other, they destroy each other in a powerful explosion, like fireworks. This means that even though matter and antimatter were constantly created and destroyed, somehow there was always a little more matter than antimatter, which is good because otherwise we wouldn't have anything left. As time went on, particles started to stick together and form more complex things like atoms and molecules. And eventually, stars formed and created even heavier elements. But someday, a long time from now, all those stars will burn out. When the last star slowly cools and fades away, the universe will turn into a dark void without life, light, or anything we know and assume there is. At some point, voracious black holes will eat all matter in space. Eventually, even those black holes will evaporate away into the tiniest amount of light. Our cosmos will continue to expand. The light will become spread out and unable to interact with anything. So, all activity in the universe will stop. Space will become a vast, empty void with no stars, planets, or anything else, and will end there. Or just begin. And maybe that's where we'll meet again.